So something very important to consider when taking geophysical measurements is that there's no point in making a measurement unless you have a physical property contrast between two rock types or within a rock type. What does that mean? If you're using magnetics, you need to have a change in magnetic susceptibility because you will actually pick up that change. If you're using gravity, you're looking at density, and so you need a difference in density between two rock types or within a rock type. Maybe there's a fracture zone, a slightly lower density. With seismics, you need a change in acoustic impedance, which can also be linked to density. And with resistivity, you need a change in resistivity or electrical conductivity. So there's no point in doing a survey in an area or looking at data in an area if there isn't a contrast.
Okay, so what you would actually do when you do the field school next year is you spend a day in the field taking rock samples and measuring the magnetic susceptibility with this instrument. We've got another instrument, and then you can then have actual values that you put into the modeling software. So as a geophysicist, we like to just have data, but you do need to go to the field. You do need to look at what rocks you're looking at. Because if you look at a textbook of magnetic susceptibility, there's orders of magnitudes that the values can vary. So you do need to go to your area, check your area. And these are the type of values you can look at. These are ones with high susceptibilities. So there's two sets of units, which you'll see in the software, CGS and SI. So usually we work with SI units, but you just got to keep it in mind. In textbooks, they often give two different values. There is a conversion between the two. It can get a bit complicated, but you just need to be aware of that. So you can see quite a range of values. You can get even more of a range than that. But this is what you're going to do on the field school next year, is actually produce these charts. So these values kind of high. We went up to about 40, some of them went up to 80. Whereas here we're going, same units here, and we're going up to the 2000s. And this is a dolerite. The dikes that we've talked about already are dolerites. And Hartsbergites are the more mafic layers at the bottom of the bushveld complex. So those are much higher values. So everyone just keep in mind, we've got 2000 times 10 to the minus 6. So it's kind of like 0.002. So that's, just keep in mind the quantity, like the values we're actually going to be putting into this modeling software. So have you guys actually spoken at all about if you went out and did a survey, like you as a geophysicist need to plan what your station spacing is going to be? Have you spoken about that at all? A little bit? Okay. And so let's imagine this is a dike that's come up, it's at an angle, and so it's got an induced field. So because of the magnetic minerals inside of it, the Earth's field induces a magnetic anomaly, and you do a profile over it, that's what the anomaly is going to look like. But how often must you take measurements along this profile? Like you can take a measurement every 10 centimeters, you'll be there all week. Or should you take a reading every 10 meters? But the reason why you've got to look at this is there's no units here, but let's assume this is every 10 meters. If you took a reading every 10 meters, so ultimately your anomaly in your data is going to look like that.
And this is called aliasing. So you're not getting your full signal, you're getting an incorrect signal because of your station spacing.
So that's why station spacing is really important. You really need to figure out how close together your stations need to be to see the full anomaly, but not go so overboard that you're doing 1 centimeter spacing. Because you kind of got to outweigh, am I going to find the anomaly versus is this going to cost a lot of money? So you can see now, if maybe we did 5 meter spacing, we would land up here, and it would still be quite a jagged jump, but at least we would be getting as high. So that's what you've got to take into account, and that's what we're going to look at today in the software. So we said already, why do we do a ground magnetic survey? To find dolerites. On the field school, it's mostly they're mining the UG2 or different layers in the bushveld, and these dikes cause loss of ground. So they can't mine there. It also might make the ground unstable. So they need to know where to put extra support in, and that's where these ground surveys come in. There's a cheaper thing you can do. You can actually do a aeromagnetic survey. Have you guys spoken yet about aeromag surveys? So putting a magnetometer in an aeroplane And so they've actually flown the whole of South Africa with aeromagnetic data. And so the station spacing you can see was 1 kilometer between each line. So that's quite far apart. And so this is in the Bushveld complex, and you can see these are dikes coming through. But this at least gives you a general idea where things are. But like, you can't tell me that you know exactly how many dikes are in here. And as a mining company, I want to know if I'm going to go into this area. So that's when you would bring in a ground magnetic survey. And so it's way more expensive because you've got to pay for people. It takes a lot longer, but you're getting a higher resolution. And this is our new system, so it's a walkmag, so you look like a robot a bit, but on his head there's a GPS. I think our GPS is on the side, and the magnetometer. So this previous one, you used to have to walk 5 meters, put it down, take a measurement, walk 5 meters, put it down. Such admin, and you'll still do it on the field school. But this new system, you literally can just walk, and it records continuously for you as you walk. And so here you can see the difference. So this blue curve is the airborne magnetic data, and you can see generally, you would say maybe there's a dike over here, whereas this red is the ground magnetic survey, and they've picked up 3 dikes. So a lot more detail. Okay, have you guys spoken about forward modeling versus inversion modeling? No stress if not. No. So forward modeling is what we're going to be doing today. So you don't just go to the field and suck out your thumb what the heck your data is going to look like. You actually put stuff into modeling software and you work with it. So forward modeling would be that I put in a body here and the software calculates what the magnetic signal would look like. And so then I go, okay, well that's what I'm going to expect in the field. If I know I have dikes in my area, then I'm going to see something like this when I go to the field. Another way of using forward modeling is to say, okay, I've gone to the field, I've collected data, and I've put that data into my software. And so my data looks something like this. So now I'm going to come and I'm going to put a body in here, and it's going to say, okay, it's going to look something like this. So I say, okay, that's kind of close. And now I play around with this body, I move corners, I make it shallow, I make it deeper, to see where exactly the solid curve fits the dotted curve. So the dotted curve is what we measured in the field, measured data, and the solid curve is the modeled data. So it's what the program is spitting out. And so what I'm doing here is that I can't know what's in the ground unless I drill boreholes, and even seismics we can't really figure it out because it's vertical. So the closest thing I can do is I can collect magnetic data and then try and create a model. And my model, it calculates what my model response is and it fits it to magnetic data, and then it says how good my model is or how bad my model is. So that's what forward modeling is. Inversion modeling is kind of, instead of you putting in this body, seeing how it fits, and then adjusting your body, you kind of click a button on the computer that goes inversion, and it completely puts a body for you. And so sometimes the body it puts in is way weird and doesn't make geological sense. That's when you as a geophysicist have to say, okay, don't change every single corner, just change this corner. I know it's going to look like a dike, I know it's kind of going to look like this. So we'll play around with that just now. So those are the 2 types. I remember being completely freaked out by the word inversion. When I was in honors, I was like, this is hectic. But it's really not. It's quite helpful. You've just got to be careful, because I think as new geophysicists, we kind of just like to push buttons. And it answers the question for us, and then geologically it makes no sense. So you've just got to be careful and just use your mind with that. So I said, you use it before field work. So it tells you what body can you resolve with your equipment. Because maybe a dike at 100 meters depth, that's like this wide, there's no way you're going to see it with your equipment. Like that's just like the minimum thing you can measure with your equipment. So it helps you know what the smallest body is that you can actually pick up in the field. Are you using the right equipment? So maybe taking a measurement every 5 meters isn't good enough. You need to use that walking one that measures, the walking magnetometer that measures more often if you're going to find a small body. It just helps you have an idea of what equipment to use. Often you've only got one type of equipment, so you actually can't change, but if you were very rich and you had lots of equipment, it'll help. Should you change your station spacing? That picture we looked at earlier, that the red dots were too far apart, you need to test that beforehand, or at least know that if you keep your station spacing at 10 meters, you're going to miss something. So you're going to get a wrong image. You're going to get that weird small anomaly instead of that full anomaly. After fieldwork, you're going to model your data. So this is called forward modeling to get an idea of what bodies are there. Magnetic data and gravity data, anything you do is a guess, unfortunately. It's often a very educated guess. You know you're going to deal with dikes, you know what dikes look like, but you still don't know. Unless you have seismic data, which you can't see vertical stuff on, or unless you've got borehole data, it's still just a guess. And so you need to know that. There's actually several models that would fit your data. Yours is not the only one, even though you think it's right. So you just need to be aware that you need to put that in your report and say more data would help you constrain your model.